Okay, here we are with section 10.6 now. This is the pH scale. That is a scale that is used to measure the acidity of solutions. Why not use concentrations? Well, hopefully you'll see at the end of this section that the pH scale is actually something of a convenience. It's a little easier to work with than the scientific notation and the very small numbers that you usually find as hydrogen ion concentrations and hydroxide ion concentrations. And you see what we're trying to get you to do here is calculate the pH of a solution from the concentration of hydronium ion, and given the pH, calculate the hydronium ion concentration. And of course, if you know that, you can, knowing the dissociation constant of water being 1 times 10 to the minus 14th, you can also calculate what we call the pOH, or also the hydroxide ion concentration. Although we're not really going to focus on those, we're focusing on the pH. The pH scale usually runs from 0 to 14, and it's used to indicate acidity. It's acidic when values are less than 7, neutral at a value of 7, and is basic when the values are greater than 7. Now, if you look at this table, the acidic solution, pH less than 7, that means the hydronium ion concentration is greater than 1 times 10 to the minus 7th. Neutral solution is, the hydronium concentration is 1 times 10 to the minus 7th, pH is 7. And the basic solution, you see, it's the pH greater than 7, it's the hydronium ion concentration is less than 1 times 10 to the minus 7th. You should see something rather interesting about that table. The pH, the pH being less than 7, it means there's the hydronium ion concentration is greater than 1 times 10 to the minus 7th. Neutral solution, pH is 7. That is also the negative of the exponent on the 1 times 10 to the minus 7. And again, it's the 7. The 7 there is also the negative of the exponent on the factor. It's the power of 10 in the scientific expression notation. That's not a coincidence. We'll get to they're going to define that sooner or later. But you can measure the pH in a number of ways. You can use a pH meter. You can use pH paper, and that's not litmus paper. It's an indicator paper that turns specific colors at specific pH values. You remember red litmus turns blue in base, and blue litmus turns red in acid. But these are papers these are indicator papers that actually will give you a little more detail on which pH you have. And you get the pH by comparing the colors of indicator paper to a chart. And here's some examples. You have the pH meter, pH paper, and you see in the pH paper the different pHs according to the color that the solution gives you when you dip the paper in. And then there's other indicators that will change color at different pH values as well. On a pH scale, if you're below 7.0, you're acidic. If you're at 7.0, it's neutral. And above 7.0 or basic. And there's a table here that gives you some examples where you start with at the top, you have a very low pH of 0. That's a 1 molar hydrochloric acid solution. Gastric juice at 1.6, lemon juice at 2.2, vinegar at 2.8. Carbonated beverages are 3.0, so they're pretty acidic. Orange is at 3.5. And then you have apple juice at 3.8, tomatoes at 4.2, coffee at 5.0. A lot of these things are acidic. Even bread, potato, they're 5 point something range. Urine is at 6. These are all acidic. You have a lot of biological materials tend to be acidic. There's a few that are basic though. Pure water is 7.0, and then drinking water is up a little higher. because drinking water typically has some dissolved, usually carbonates dissolved in them. Blood plasma is a little higher than that, and bile 8.1. Detergents are 8 to 9. Seawater is 8.5, so seawater is a little bit alkaline, a little basic. Milk and magnesia is even higher yet. Ammonia is, I'm assuming that's ammonia solution, because ammonia is actually a gas. So it's ammonia. This would be household ammonia or something like that. What they have there looks like Windex. It's ammonia D, they call it. Bleach is pretty high, 12.0, and then 1 molar sodium hydroxide is 14. So that's the scale from 0 to 14. So now we have a learning check here. Why don't we want to identify these solutions as acidic, basic, or neutral? We have hydrochloric acid, HCl, with a pH of 1.5. And you notice we had, go back to this last table, 1 molar hydrochloric acid solution is at 0. And now we have a hydrochloric acid solution with a pH of 1.5. What's going on? Well, the pH is going to be determined by the concentration of the hydrogen ion. And since hydrochloric acid is completely dissociated, you're going to have a different, well, you have different concentrations that are going to give you a different pH. So, well, we know that's acidic, pH of 1.5. Pancreatic fluid is 1 times 10 to the minus 8th. Now, that the concentration of 1 times 10 to the minus 8th, that is less than 10 to the minus 7th. So now you're looking at see, that's going to be a little bit basic. So they're throwing a couple of different terminologies at you. They're throwing pH here. They're throwing the hydrogen ion concentration. So you have to think about these. Well, pancreatic fluid, it's going to be basic. Sprite, soft drink, pH is equal to 3. Well, they come out and give you that the pH is under 7 is going to be acidic. pH of 7.0, that's neutral. And then you got hydroxide ion concentration of 3 times 10 to the minus 10th. Okay, now there is that's a little bit of a curveball, because you're actually looking for the pH, whether it's acidic, basic, or neutral, is going to be kind of defined by the hydrogen ion concentration. But you can think about take a look at the hydroxide ion concentration here, 3 times 10 to the minus 10th. You can do a quick calculation. Let me do this calculation. Remember, in the last section, we were doing some problems like that. And you can do this in 2 ways. You can recognize the fact that 3 times 10 to the minus 10th is quite a bit lower than 1 times 10 to the minus 7th, which would be neutral. So if the hydroxide ion concentration is lower than the hydronium ion concentration, has to be higher, so you're suspecting acidic there. If you actually do the calculation, you find that it's 3.3 times 10 to the minus 5th is the concentration of hydronium ion. So that is going to be acidic. And a hydronium ion concentration of 5 times 10 to the minus 12, well, that's way below the 10 to the minus 7th of neutrality, and less than hydronium ion concentration, less than that is going to be basic, because if you calculated the, in fact, let's go ahead and calculate the hydroxide ion concentration. And 5e to the minus 12. You get a 2 times 10 to the minus 3rd. So that's the hydroxide ion is much higher than 10 to the minus 3rd, or 10 to the minus 7. So that's a basic solution. So let's see if we, let's write these things down here. HCl, that's acidic. We agreed to that. Actually, this isn't giving me anything. Acidic. Oh, I can't. It won't let me write on here. Okay, so let's just take a look at these and see what we got. You know, HCl is acidic. Pancreatic is basic. The soft drink is acidic. pH is 7 is neutral. We mentioned this was acidic, and the hydroxide was acidic, and the hydronium ion concentration was basic. Notice what they did there with those last two. They were maybe not really trying to fool you, but seeing if you understood that dissociation constant of the ionization constant of water, because the hydroxide is a base, hydroxide ion is basic, but the concentration of hydroxide ion in water is going to give you information about the hydronium ion concentration of water, which is actually what defines whether it's acidic or basic. And it's that 10 to the minus 7th cutoff in what direction, which side is it on? Is it greater or less? Hydroxide, you're going to have more hydroxide in basic solution, less hydroxide in acidic solution. So this is less than 10 to the minus 7th. And the same with hydronium ion concentration. You have much less hydronium ion than you would have in pure water. So there has to be quite a lot of hydroxide to compensate for it. These are trends that you need to be aware of, and it can be a little bit of work. Okay, here's the deal with the pH scale. You notice that pH is 7 with a 10 to the minus 7th hydroxyhydronium ion concentration. Well, this is a logarithmic scale, the pH scale. And the pH is simply the negative logarithm, the negative base 10 logarithm of the hydronium ion concentration. So pH is equal to minus log hydronium ion concentration. So to calculate the pH, the negative powers of 10 in the molar concentrations are converted to positive numbers. So if the hydronium ion concentration is 1 times 10 to the minus 2, it's the negative logarithm of 1 times 10 to the minus 2. So it's going to be equal to 2. In this case, your logarithm is minus 2, so the negative log is 2.0. So remember, there's what am I trying to say? There's that conversion, there's that changing the sign of the logarithm of the hydronium ion concentration. So let's look at this. To determine the number of significant figures, you consider the following. Okay, the number of decimal places in the pH value is the same as the number of significant figures in the coefficient of hydronium. So the number to the left of the decimal point in the pH value is the power of 10. All right, so the power of 10 is really not, it doesn't come into the play. As far as scientific notation goes, the power of 10 does not determine the number of significant figures. It only determines what the number is to the right to the left of the decimal point, and that's pretty much it. So here we have some of these pH values, and you can write these with some of these. You can write off. You can write them off from just knowing the pH. You just you know that it's an exponent of 10. So a change of, and now there's another important thing though. A change of 1 pH unit corresponds to a 10-fold change in hydronium ion concentration. So you see what's happening here. Your pH of 2 is 1 times 10 to the minus 2. pH of 3 is 1 times 10 to the minus 3. pH of 4 is 1 times 10 to the minus 4th. So as the pH goes up, the hydrogen ion concentration goes down. But these are factors of 10. And of course, if you go down, if you have pH of 1, think about that. A pH of 1 is going to be, well, in fact, let's do a couple here. Let's go into some extremes here. In the previous slide, you see we had pH of 2.0. It means you've got a hydronium ion concentration of equal to 1.0 times 10 to the minus 2 at pH 1.0, this is going to be 1.0 times 10 to the minus 1. So this is going to be 0.01. This is going to be 0.1 molar. And you can have a pH of 0. Okay, you can have a pH of 0. And that's going to be 1.0 times 10 to the 0, which is equal to 1. Okay, so 1 molar. And you can get that. And you can even have a pH, you can even have negative pHs in principle, although you're not going to see that very often, because this is going to, if you think pH of 1, it means you're going to have a 10 to the 1, 1.0 times 10 to the 1, which is going to be 10 molar. Although you can get 10 molar concentrated acids at 10 molar. But that's just an aside. These are factors of, essentially they're factors of 10. A change, 1 pH unit is a factor of 10, one way or another. So just keep that in mind. Be aware of that. And go on here. Now you can calculate a pH from the concentration of hydronium ion. Okay, so you take aspirin at 1.7 times 10 to the minus 3, a solution of aspirin, 1.7 times 10 to the minus 3. What's the pH of the solution? Well, it's a negative logarithm of 1.7 times 10 to the minus 3. So with a calculator, scientific calculator, can be simple. You're given the 1.7 times 10 to the minus 3, and that's your, now you get the pH. So you need the pH equation. What's the pH? The pH is the negative logarithm of the hydrogen ion concentration. So all you do is you input the hydrogen ion concentration, which is 1.7 times 10 to the minus 3, and you take the logarithm of it and you make it negative. So you do 1.7 calculator display. You see what they're doing there. 1.7 times 10 to the minus 3. In fact, let me actually do this for myself so I actually see the calculator doing it, because this thing here looks a little funny. So no, it's okay. That one's okay. Okay, so these are the steps you take. You put in 1.7, and then you hit the double E or exponent. You're going to get one of these numbers, and then you change the sign of the exponent, and then the calculator display is going to be this, 1.7 times 10 to the minus third, and so forth. Then all you do is you hit the log key, and that's going to give you a display which is going to be, well, then you hit the log key, that's going to give you a negative number, and then you're going to change the power of that, and you're going to get that number there, and it's going to be the 2.769 and change. Then you're going to you're getting the negative. Then you're going to have to round that. Okay, you go through these steps. You get 2.76955 and so forth. Well, you only get, remember, 1.7. You only get two significant figures there, so you have to round that. So it looks like it's going to be 2.8. Or 2.7. I'm sorry, 2.77. Okay, number of significant figures, just number of significant figures on the right of the decimal point. Okay, so it's okay. So the units value in the 2.77. Okay, I was wrong about that. It's after the decimal place. So that 2 points in that 2.77 where they've rounded it off. The 2 is exact. It's essentially 2 plus 0.77 or something similar to that. Actually, it's a little more complicated than that, but so it's 2 decimal places are a significant figure. So it's 2.77. Okay, so we find a solution of solution with a hydrogen ion concentration of 4 times 10 to the minus fifth. Now this should be fairly simple. Okay, this should be fairly easy for you. You take 4e to the minus fifth, you take a logarithm, you're going to get a negative number, and you just make it positive, and you're going to get 4.39, something like that. Somewhere 4.39 something. We'll see it on the next slide. Okay, 4.0, you take the pH equation, and you go through all these steps, and you're going to get 4.3979 and so forth. You have 4.0. You have, that's the coefficient of in the scientific notation. That number of significant figures is what you have after the decimal place. And so you're going to have to round this off. It looks like 4.40 is going to be your answer. And that's what it is. So that's the way you do that. It's really a fairly straightforward process. Now, okay, given the pH of a solution, we can reverse the calculation to obtain the hydrogen ion concentration. So how do you do that? You take 10 to the negative pH. So for pH values that are not whole numbers, the calculation you have to use the 10 to the x key, which is usually a second function. Although I think there's you can use an anti-log key as well, but you can use the 10 to the x key. So let's do these here real quick. Determine the hydrogen ion concentration for the following pH values. Okay. So 3.0 is, you're going to do, in my calculator, it is a 10 to the x function. So second 10 to the, oh wait. Okay, type in 3.0 and hit second 10 to the x and you get 1,000. Well, I forgot to change the I forgot to change the sign of the 3. So let's do that again. Now, okay, I did that. Now it's 1,000. Okay, so 1 times 10 to the minus 3, and then 3.42. That's going to be, doesn't look right. Negative second 10 to the x. Maybe it is right. Got that the second time. So what I get here is, put that in scientific notation, I get 3.80 times 10 to the minus 4th. Okay, actually it would be 3.8 times 10 to the minus 4th is what I'm guessing it's going to be. And of course there's the 1 times 10 to the minus 3 and calculator display through this one here, 3.42. So you're going to have to round this, and it is 3.8 times 10 to the minus 4th. So this is, you need to watch that. It's going to be easy to be confused in the pH value, where they say the pH value of 3.42 is 2 digits on the right of the decimal point. The pH has 2 digits to the right of the decimal point, and that's the number of significant figures in the scientific notation form. So that is something you have to watch. Watch your significant figures, because I have to consciously think about that myself. Some of these things sink in, no matter who you are. Some of these things sink in pretty easily, and some of them are a little more painful. So you need to pay attention to those. And anyway, there's your comparison of pH and hydrogen ion and hydroxide ion concentrations. Okay, so that's the lecture part of this. I'm going to go over to the text, and I'm going to pick out some problems. I'm going to work them and see how they come out, so you can see this being done. So let me get reorganized here, and I'll see you at the whiteboard. Okay, I'm back. I'm going to work on this one, 10.39. Calculate the pH of the solution given the following. And we have state whether doesn't look like they ask you to calculate any hydrogen ion concentrations from pHs. We'll take a look later on, see if I can find some of those real quick. But anyway, 10.39, calculate pH. We have, okay, hydrogen ion concentration is A, B, C, D, E, F. Okay, there's a lot of these things, A, B, C, D, E, and F. And you've got a hydrogen ion concentration of 1 times 10 to the minus fourth. We've got a hydroxide ion concentration. When I say hydroxide ion concentration up here, I meant hydronium of 1 times 10 to the minus fifth. C is, oh, that was wrong. That was, that's not what I wanted. Well, let's grab this here. Nope. Stop that. And that was C. So let's move that down there. Okay, now let's go back to B. Is hydrogen ion concentration equal to 3 times 10 to the minus ninth? 3.0, no, that's, yeah, just 3. Now let's get this out of here. These are all molar. D is 2.5 times 10 to the minus 11th. Yeah, that's a hydroxide. 2.5 times 10 to the minus 11th molar. And E is hydronium ion concentration. And that is 6.7 times 10 to the minus eighth. Right, here's 1039. And lastly, we have hydroxide ion concentration of 8.2 times 10 to the minus fourth molar. Okay, we're supposed to calculate the pH of these. Well, let me use a red pen here. This one, and this one really aren't going to take a lot of doing. You just take the logarithm. Well, actually, a couple of these you could just write them out right off the bat, but you will take the you need to take the logarithm, and then having the logarithm, you make it negative. So you get out your calculator, and let's just go through these. The first one, the H0 plus, you take 1e to the minus 4 and take the logarithm of that. You get a minus 4. I mean, you can already see that you realize that minus 4 is the exponent on the 10 there. And you're going to have to change that to a negative number. So this one is going to give you 4. And you see here, there's only one significant figure here. This is, well, 4, and it'd be 4.0. Remember, this 4 is the exponent. And we do the same thing with 3 times 10 to the minus 9th, 3 e to the negative 9. And take the log of that, and you get a minus 8.5 something, and you change that to negative, and you only have, okay, 8.5, so it's going to be the 8, get 8.5. Okay, the 8 is an exact number. That's the 8 is really from the exponent, and the 5 is defined by the one significant figure there, so it's going to be 8.5. We'll go down to E, 0.7, e to the minus eighth. Take the log of that, and I get minus 7.17 and so forth, and make that negative. And we get 7.1 something. I get 7.1739. And here we've got these two significant figures now. So you're going to have the 7, which is the exponent, that's from there. And then you're going to have two significant figures here. So you get 7.17. I'm giving you practice on that. Okay, now, there's a couple of ways you can do this, the C, D, and F. So one of the ways you can do that is you can actually take this logarithm and you can take the POH and subtract it from 14, and that would be the pH. Or you could use the case of W. Okay, so you know that to get the hydrogen ion concentration here, it's going to have to be is equal to 10 to the minus 1 times 10 to the minus 14th divided by, it's the 1 times 10 to the minus, is that 10 to the minus 5th? It looks like it. I'm going to say C. Yeah, it's 1 times 10 to the minus 5th, so it's 1.0 times 10 to the minus 5th. We do that calculation. And we're going to get a really monstrous number there. And we're going to have to convert that to scientific notation. Then we take the log of that, and that's a minus 9. So that turns out to be minus 9. So the pH is going to be 9. Okay, this is going to be, where are we here? This is going to be 1.0 times 10 to the minus 9. Actually, it really should be, I really should only be using one significant figure here, right? 1 times 10 to the minus 9. So, well, let's, I'm not going to erase all these things, but I should be using 1 times 10 to the minus 9 here. So that's going to be, now you take the log of that, and you see, well, you take the logarithm of that, you see that the pH is going to be, the logarithm of that is going to be minus 9, and the negative logarithm is going to be 9. So the pH is going to be equal to 9. Okay, there's only one significant figure here. Or actually, no, 1 times 10 to the minus 50. Yes, okay, this is the okay, this is the exponent. This is going to be after the decimal place. Now, so I did have this correct. Okay, so this is 1.0 times 10 to the minus 9th. Remember the exponent is what's is 9.0 here. No, this, I got to back up. This is 1.0. 1 is, okay, this number is after the decimal place. This is the units. That's the first, that's the digit to the left of the decimal point. And then this one here, and there should only be 1. Okay, I did this wrong. This should be 1 times 10 to the minus 9. Okay. And then E 7.17. Or wait a minute, that's correct. Okay, so this one here, now we're going to this one here, the 2.5 times 10 to the minus 11th. Okay, so now we're going to have two numbers after the decimal point here, and we need to take but we need to first do this calculation. Is equal to 1. I keep doing that. It's 1 times 10 to the minus 14th and divided by 2.5 times 10 to the minus 11th. This 1 times 10 to the 14th, this one is essentially exact. So when we do that calculation, you get 10 to the minus 4th, or you get 4 times 10 to the minus 4th. It's going to be actually, it'll be 4 point, well, yeah, 4, be 4 point, actually be 4.0 times 10 to the minus 4th. This here. And then you take a logarithm of that, you get minus 3.39 something, and then you take the negative, and you end up with 3.397 something, but you had these two things here, so that's going to be, you're going to have two numbers after the decimal point, so you're going to have 3.40. Should be the pH. And then, well, we've already calculated this one. Now we have the 8.2 times 10 to the minus 4th. I'm going to show you another calculation here. Okay, the actually, no, I better not. That could be more confusing to you. Let's just keep working through this the way we've been doing. So the H3O plus is equal to 1 times 10 to the minus 14th. Then we have divided by 8.2 times 10 to the minus 4th. And remember, I'm doing this, and I'm kind of doing this fast because, you know, let's say this is a quiz or something like that. You really don't have time to write all this stuff down. You have to know which number is which, and that's not exactly necessarily ideal, but that does force you to get more attentive as to what you're working with. Divide up by 8.2 times 10 to the minus 4th, and we get, that can't be right. Type something in wrong. 1e to the minus 14th divided by 8.2 e to the minus 4th equal, that makes more sense. I get equal 1.22, well, 1.2, never mind, 1.2 times 10 to the minus 11th. So your pH, you take a logarithm of that, and you get a minus 10.9, and you take the negative of that, and so you get 10 point, it looks like 10.91. All right, so there's our answers. And let's see how they check out. Let's box the answer. We used to be told to box your answers when you do a homework problem. So these are the that and that. Do I have 6 of them there? Let's see. Okay, 1, 2, 3, 4, 5, 6. Okay, they're all there. So now we take a look at the what the book says. Okay, you look in the answers in the back. They all check out there. There was one that didn't check out. And let me look at this one more time. The one that didn't check out was F. The book has 10.92, which is, it's not that big a difference, but I do want to take a look at that because maybe I got the wrong, no, 8.2 times 10 to the minus 4th. Okay, I got, the number I got was negative, the logarithm was negative 10.9138. So that, by the calculation I did, 10.91 is correct here. So that might be a little bit of a typo in the text. I don't know, but that's this seems to be correct. So that's the way that's some of these problems. I'm going to try to get some over the weekend. I'm going to try to get some other problems worked out for you, and but that'll do for now. So I'm going to stop this one here, and now you've seen the you've seen this here. That's also in the text. So we'll move on to section 10.7 next.